Hello, everyone. Can you hear me okay? Yeah. Okay. I will start with a small joke. Since I am from Cairo, and I obviously have a ton of respect for all of my colleagues here at the University of Alabama and at the National Water Center. However, the best forecasters in the world are from Cairo, Egypt. And I'll tell you why. Because we have total annual rainfall of 10 millimeters. That's 1 centimeter. So I can tell you from now the forecast for the next 4 months is going to be sunny, no cloud on sight. In the morning is going to be, or the daytime is going to be 70, and at night is going to hover around, the daytime is about 90 degrees, and in the evening is going to be 70. And I will be correct. So there is absolutely no dispute about that. Our forecasting job is very easy in Egypt. Now about this topic here. I will focus actually in coastal regions. I do quite a bit of work in coastal Louisiana and also in the Everglades, Florida. I've also done a bit of work in the Mekong system. And it's amazing actually how universal the same challenges or the challenge that we face in these coastal regions. They have a little variations from one location to another, but for the most part, very similar challenges. And it's always an interesting complexity between cultural issues, economic issues, and environmental value issues of these ecosystems. So this slide here is from South Louisiana. Louisiana in particular is what we call a working coast. We don't have beach resorts or anything like this. There's a lot of, the coast supports a lot of jobs. It has very important cultural value, and it has a huge economic value because remember the South Louisiana does have the mouth of the Mississippi River with a huge industry relevant to navigation and port systems. So I will focus today on two small elements of the coast, which is oysters and marine mammals, basically dolphins, and we'll talk about that. This is here an image about marine mammals or dolphins, and those pink dots that you see, each one of the dots is one particular animal, and we observe how they swim around, and they are protected by something called Marine Mammal Act. And there is some restoration projects that are being pursued by the state that will influence the salinity regime, and unfortunately it will influence these animals. And it's very important for us to make sure that they're going to be okay when we implement some of these strategies. So some of the work that I will share with you today is discussing about how can we actually accommodate restoration targets as well as protecting some of these natural resources. So this is one of the things that we will add complexity to the system. Before we proceed in terms of, okay, what should we do to do these studies, I'm promoting something, and it's a very common theme now. It's called co-development of science tools. Basically, you identify what we call the domain experts, scientists and engineers, and from various disciplines, but they need to also work with the local knowledge because people who live in these areas and manage these areas have a lot of important knowledge that we need to harness. And I can tell you the worst thing to do when you want to actually engage with the stakeholders, a guaranteed approach to fail is to do this. Walk in the room as a scientist and engineer and tell people, define the problem for them, tell them what their problem is, tell them what the solution should be, and also tell them what tool they should use. As soon as you do that, you already alienated them from participating. They feel intimidated, they feel disconnected, and they feel that you already are on your way to define what the issues are going to be and how are you going to solve it, and their participation is an afterthought. This is actually common in a lot of state and federal efforts when the plans are being done by scientists and engineers with the best intentions, and then they presented in public hearings. But then guess what? When somebody stands up and say a comment, what can they do at this point in time? The work has been done. And the people who are voicing their opinion, they know that it is going to be very difficult for them to incorporate these opinions. So we got a planning grant to actually pursue that co-development. And this is the topic of what we are going to be doing today is how can we co-develop forecasting and management tools for coastal Louisiana for this particular application is to manage some natural resources in the Gulf of Mexico. Before I proceed, I want to acknowledge my research team. They are the people who do most of the work. I mentor and guide, but I want to thank each and every one of them. It's a collection of full-time researchers, graduate students, and undergraduate students. For this co-development effort, we actually engaged with a lot of federal agencies, state agencies, NGOs, private sector, so that we can engage natural resource managers and the development of these tools. So we went through an effort where we defined what the issues that we want to focus on. We want to focus on oysters and marine mammals, and we started to ask these managers, what do you need? What kind of information do you need in order to manage these resources effectively? And how fast do you need the information to come to you? What kind of visuals that you would like to have? How do you want the information to be organized? What are the temporal and the spatial scales that you need? We engage them in every aspect of designing the tools that we will pursue in order for us to produce information for them. And we went through series of workshops. We had a 3-day charrette intensive meetings so that we can harness that input from them. And you would be amazed at actually how specific they are in terms of exactly how they want the information so that it can feed into their day-to-day decision making. When the science tools are so intimidating and prohibitive for them to pursue, they fall back into their gut feeling or experience, and they have to make decisions. They cannot wait. It's also very tiring for them to always have to contract a consulting company or a university to do a study for them that will take months, sometimes multi-years, in order for them to get information. And every time they want to change or adjust the scenario, they will have to go back to the contractor to do that. So the idea here is we wanted to make that science tool accessible to them so that they can interact with it directly, make adjustments as much as possible, run scenarios that they want, rather than to continue to be dependent on a university or a contractor, private or public. So that was the idea of that co-production effort that we did. We're still continuing to work on this project as we speak, but I just wanted to share the effort that we have gone through up until this point. This is the domain of interest, or the area that we are interested in. The north central part of the Gulf of Mexico, especially the coastal area of Alabama, Mississippi, and part of the Louisiana coast up to the Atchafalaya River, basically. That area receives a lot of fresh water, mostly from the Mississippi River, but there are several primary rivers that actually contribute quite a bit. One of them is the Mobile River. One of them is also the Pearl River in the border between the state of Mississippi and Louisiana. And then obviously the big river is the Mississippi, contributes a lot of water. Most of these rivers are natural, so there is not a whole lot of management that we can do, but we wanted to include them into our model. The management is going to happen mostly on the Mississippi because it's the one that does have engineered features that you can actually turn on and off these knobs. So we wanted to study the Mississippi in the context of the existence of all of these other rivers as well. So there are a number of existing already engineered features on the lower Mississippi. Some of them are for restoration purposes. Some of them are for what we call flood risk management. And they are very large structures that release a lot of pulsed fresh water. And there are more planned by the state of Louisiana that will be coming online in the next few years. One particular structure that I want to talk about today is the Bonnet Carré Spillway. That structure was built in the early 1930s as one of the actions that the U.S. Army Corps of Engineers took in response to the 1927 flood and the build-up of the Mississippi River and tributary levee system. That's what it looks like. It's a very old structure. Whenever they want to open it, they will go with cranes and remove wood logs to open the gate. So it actually takes several days for you to open the structure. And it does connect the Mississippi River. That's the Mississippi River right here. It goes from left to right, and the water will come off. When they decide to open it, it will come up like this, in this direction here, if you can see my mouse, and then it puts water into Lake Pontchartrain, and you can see here the plume. This was one of the recent openings in there.
The mouse wasn't moving. Would you mind pointing at the screen with your finger or something?
Okay, let me see.
It didn't show the cursor.
Okay.
I'm not sure why.
Is there a highlighter or anything that I can use? I can use here so that the camera can. So the Mississippi River flowing in this direction, and the water comes out. This is the structure right here. So the water will come up and go into Lake Pontchartrain. Lake Pontchartrain is brackish, but it's directly connected to the Gulf. So ultimately the fresh water will completely freshen the lake and actually will freshen Mississippi Sound as well. So this is a record of how the U.S. Army Corps of Engineers manages the lower river. I don't want to bore you with all the details, but they have what they call the design flood, which is 3 million cubic feet per second, and they have authorization to manage the river when that discharge is happening. So they have an allocation to each one of those knobs or faucets that they will open up to relieve the pressure from the river. The Bonnet-Carré spillway, the focus of the talk today is this one right here. It has a capacity, nominal capacity of 250,000 cubic feet per second, a lot of water. The other one that they don't operate often is the Morganza. Morganza takes water from the Mississippi River and put it into the Atchafalaya system. The Atchafalaya system is a freshwater system. So could we put fresh water into a freshwater system? Wouldn't that be better than putting fresh water in a brackish marine system? We'll talk about that. Here is a record of how of all the openings that happened in the Bonnet-Carré since inception or since construction. It doesn't seem that they opened it too many times, given it's almost 80, 90 years now since they built it. But if you look at the last decade in particular, that's a lot of openings for the last decade compared to any other previous decade. So it's a lot more than typical. It's also the first time ever that they open it in 3 consecutive calendar years, 2018, 2019, and 2020. Never happened before. It's also the first time ever that they open it twice in the same calendar year. That never happened before. Also, this last decade experienced the earliest pulsing from Bonnet-Carré in January 10th. Never opened that early in the year. And then last one, they never opened it in July before, that late in July. The problem with opening in the summer, the estuary is very productive. So usually if you open it in the winter, things are a little bit dormant. You're not causing a whole lot of harm. But when you open it in July, the temperatures are high. There is more possibility to actually cause harmful algae bloom, HABs, and so on. So it's problematic when you open it in the summer. So I'm not saying that that's the new norm, that now we're going to have to open it like this, but it was important enough to bring that topic into and bring a lot of attention to it. And every time they pulse it, that 2019 pulse by itself caused the damage of roughly, some of the economists calculated about 90 million loss of fishing industry for the 3 states combined, Alabama, Mississippi, and Louisiana. So that's a lot of losses and a lot of impact on the commercial fishing industries. So they started to have discussions with the Corps. Could you alter the operation of Bonnet-Carré? They cannot, because that's a law coming from Congress. So if you talk to the technical folks at the Corps, they will tell you, please go to talk to Congress so that they can authorize us to study it. Well, the good news is they just did. So there is a brand new study that is coming down to the U.S. Army Corps. It's called the Comprehensive Study, that they are authorized now to study the entire lower river, including several states, and I think about 8 districts along the length of the Mississippi River. And they will now look at the operation of the connection between the Atchafalaya and the Mississippi, which is called Old River Structure, at Morganza, at Bonnet-Carré, and look at how they are being operated. All the philosophy that is operating today happened in the 1960s. So certainly now the Corps has much better tools, have much more knowledge about the river. So hopefully we can actually optimize this operation a bit more. From our end, we are planning to do some scenario analysis and feed it to the comprehensive study from the Corps. Some of this work here is funded by NGOs, advocacy groups, Environmental Defense Fund, and Mississippi River Delta Group. They give us some funds could you run some scenarios so that we can feed that information into the Corps for them to consider. So we designed those 10 scenarios in here about adjustments and collectively managing the restoration diversions. And we're gonna run that under 3 Mississippi River hydrographs, a wet year, let's say 2019, a typical year, which is 2021, and a dry year, 2022. It's interesting, actually, that within these last 3 years, we experienced one of the most severe droughts and the most severe floods. So if you add up the 10 scenarios that I showed in the previous slides under 3 hydrographs zone, we have 30 scenarios in here. But then also as input from the natural resource managers that we worked with, they don't want us to show discharge hydrograph and water level hydrograph. Could they say, could you actually express the output of these scenarios in a scorecard kind of format? Express the output in terms that we can actually understand and comprehend, and it feeds into the decision making. Could you translate the hydrodynamic and the salinity and the habitat suitability indices, whatever parameters you run, translate that into impacts on the system itself? So in response to their input, we are going to have that scoring, and I will show you here the metrics that we're going to use. Flooding communities. So we are actually going to evaluate impacts on flooding communities that are within that model domain. We're going to look at impacts on flooding the marshland itself. If you're not aware of it, if you excessively inundate marsh, especially the brackish and the salt marsh, you can kill it. So we need to actually calculate what we call a hydro period or something like that to evaluate, are we going to be damaging marsh or not in terms of environmental impact. We're going to look at the potential to create new vegetated land, creating new marsh, because that's a direct restoration target. So we're going to evaluate that as well. We're going to look at the oysters and the marine mammals. And let me give you an example of how are we going to evaluate the impact on marine mammals. Some marine mammal experts recently put out a evaluation metric in terms of, they said dolphins don't like, that particular species, by the way, they don't like to stay in fresh water for extended periods of time, specifically any salinity level below 5 parts per thousand. So when we run our model, we keep track of what we call the longest streak. So we calculate for every point in the domain, points or areas that have consecutive days of salinity lower than 5 parts per thousand. And then we draw a map and show the areas that are suitable for them to live. And then with every scenario, we can see, are we decreasing that area or the suitable habitat for them or not? And that's how we can evaluate the impact on marine mammals. There are similar indicators for each one of those metrics. And then we will combine that, and we are going to express it in very simple terms. If we are maintaining the conditions as they are, we give it a score of, let's say, 3. If we are worsening it, we give it a score of 1. If we are improving it, we give it a score of 5. And then we can aggregate that. So we're trying to express it in terms of a collective score, but they are also, we have the ingredients on particular resource that someone is interested in. So this is an attempt from us to translate some of these scientific output into something that can be digestible by natural resource managers. Here is an example I will show you about running alternatives. And let me preface that by saying it's going to be very difficult to find a silver bullet, an alternative that improves everything. Unfortunately, it's always a trade-off. Always a trade-off. If you try to improve things for navigation, you're going to worsen it for the environment. If you try to improve for the environment, you're going to worsen it for something else. Unfortunately, the ideal conditions for navigation is different from the fishing, is different from the environmental or the best conditions for marsh creation. So there will always be a trade-off, but our job as scientists is not to necessarily endorse certain or be advocating for certain strategies, then we will cross the line. I always consider my job is to provide information. If you take this action, here is the output going to be. If you take a different kind of action, here is the output is going to be. If you take no action, here is also the outcome. And then express the impacts and the benefits, and then let decision makers see if they can they actually endure these impacts for the sake of these benefits or not. That's not the job of the scientist. In my opinion, is to provide information for the different scenarios is the best role for ourselves. So here is a couple alternatives that we did for demonstration purposes. We ran the 2019 as a flood event, which is the historical, and here is how the flood risk management structures were operated. And then we created two hypothetical. These are not real. Alternative 1 and alternative 2, they are completely hypothetical. We took the water from putting it in Bonacary, and instead of wasting all that fresh water and sediment that goes into the Gulf and we make no use of it, we said, okay, assume that we will actually open Morganza instead, which takes fresh water from the river, put it into a freshwater environment in the Atchafalaya. And by the way, that may create problem for the Atchafalaya Basin. There will always be a trade-off. But we just wanted to see what are the outcomes. We used two nested models in order for us to globally evaluate that impact. We have a model that goes from the middle of the Atlantic and includes the entire Gulf of Mexico. And we use that large model to provide boundaries to the regional model, which is that dark blue that you see there in the middle of the screen, which this is our regional model. So we run them sequentially. The larger model gave us boundary for the regional, and then the regional, we use it to calculate hydrodynamic salinity, temperature, water quality, sediment transport, and some select habitat suitability indices specifically for oysters and marine mammals. And let me just show you an animation of the difference between two alternatives. So this animation here is a difference between what happened historically and one of our alternatives. Anything that you see blue here, that's the sediment that was wasted in the historical event, and now we are saving it because that doesn't, we rerouted the water. All the yellow is the alternative that we are promoting. This is not necessarily the best alternative, but we're just showing as an example, if you actually play with these structures, you can actually benefit from some of these resources. So that sediment in the yellow area that you see in the screen, these are areas that are starving for sediment. So instead of wasting the sediment to go to the Gulf, now we placed it in fresh swamp areas in upper Barataria and in Maurepas Basin that they can use it. And we saved all that blue sediment that used to go out. Now we're sparing that and putting it in better places. So that's one example to demonstrate the trade-off between different alternatives. This is a static map here just to show the sediment retention. So instead of all that wasted blue, we put it in the yellow areas. That's fine. But look at also at the salinity. This Mississippi Sound area here was overly freshened in 2019, and that's where most of the damage to the fishing industry occurred. So the alternative that we did helped to recover that salinity a little bit. So that's good in one sense. But look at Barataria. We over-freshen Barataria. So we fixed the problem somewhere, but created a problem elsewhere. Like I said, it's always a trade-off, and it's difficult to find an ideal situation for everybody everywhere. There will always be trade-off. But that's the good thing about models that can actually give us information about different possibilities, so we can try to see what can we and we cannot live with. I will show another example about compound flooding. These same advocacy groups asked us if we actually lose Maurepas Lake, which is in this area right here. Because of sea level rise and climate change, salinity may come in and intrude too deep into this area. The vegetation there cannot handle elevated level of salinities. So if we don't take good care of it, we may lose that vegetation cover. So could you run some analyses to show the impact if we lose that vegetation? What would happen to storm surge, for example? So that's what we did. We set up a model that encompassed the watershed that drains into the lake, and then also the coastal area, the immediate coastal area that is connected to Lake Maurepas. We used Delft FM as a vehicle for us to do that analysis, and these are the forcing data. The model does include water level, the riverine inflow, direct rainfall, wind conditions, and then we obviously have a spatial roughness map to represent the different land uses. Then we calibrated this model for 3 events. One is a pure rainfall event in 2016. It was a substantial rainfall event of over 20 inches that affected a lot of parishes in South Louisiana. In South Louisiana, we call them parishes instead of counties, but it's the same thing. We also calibrated the model for 2018, which is a riverine flood event. And then a third calibration, we calibrated the model for Hurricane Isaac that happened in 2012. So this way, at least we are a little bit comfortable that the model can reproduce coastal processes as well as inland hydrologic processes as well. So, and then we subjected it to a number of scenarios. The 3 events that I mentioned, 2016, which is mostly rainfall, 2012, which is a hurricane event, and then we created a synthetic event. It doesn't exist. We took the rainfall from 2016, added it on top of the wind from 2012. That event never happened, but we just created it ourselves as a synthetic compound event. And then we also said, okay, what would happen if Bonacari is also open? Because restoration projects, the state will have the full flexibility to shut it down if we know there is a hurricane coming. There is no need to operate a restoration diversion then. But if there is a large river flood that is happening, even if you know a hurricane is coming, what are you going to do? You can't keep Bonacari closed. You're going to flood New Orleans. So you have to open it. So what would happen if you have a flood? And by the way, that almost happened in Hurricane Harvey. If Harvey have swerved a little bit east, my brain doesn't function, by the way, when I think about left and right and east and west, because I use both hands. So if you ask me where is your right hand, I will freeze for a little bit and say, oh, okay, this is one. If Harvey would have swerved a little bit east, we would have had to open because the river was so high. It would have had a major problem, actually. But anyway, and then we subjected the model to all of these events under existing conditions, today's landscape conditions basically, and then we added a sea level rise of 35 centimeter, which is approximately the estimated sea level rise that will take place in 2050. And then we also repeated that exercise, but completely removed the vegetation cover from Maurepas. Assume that sea level rise is going to happen. We're not doing a good job and we're not taking care of it, so we will lose that cypress fresh swamp completely. So what would happen to the surge heights if that would take place? So we ran the 2016, which is a pure rainfall event, is going to be pretty difficult for you to see the difference. So let's just go to the difference map. This is the difference map for the existing condition, and a difference map for the existing condition plus this is the sea level rise minus existing condition, and sea level rise plus vegetation loss minus the existing condition. Interestingly, if you lose the vegetation of Maurepas, you make things better for rainfall because you removed all that resistance, so it's going to be easy for you to drain. Not the best message we want to send to people, but like I said, it is what it is. Because you reduce the roughness, and that's almost at the outfall of that watershed, you remove the friction, so it's kind of intuitive that, okay, you're going to facilitate draining. That's fine, but let's look at the 2012. If you ran Hurricane Isaac for existing condition, and then with sea level rise, and then with sea level rise and vegetation loss, a very different picture. If you actually, just from pure sea level rise of 35 centimeter at the edges, that will translate to about 50 to 60 centimeter in Lake Maurepas. But if you actually lose the vegetation, then you're talking about over a meter. So it's a substantial increase in surge heights if you lose that canopy cover from Lake Maurepas. There are several communities, and you're not too far from Baton Rouge, so that's a major problem. So these are the kind of analyses that will highlight the importance of taking care of that coastal system, because it does it does reduce or absorb energy from storm surge propagation. And then we did the same thing with compound event, but again, I don't want to take too much time. The analysis here is what we are trying to show in terms of the importance of that canopy of Lake Maurepas. So again, this is sea level rise minus existing condition and sea level rise plus vegetation loss. And then now we try to isolate the different drivers of that system. So here, if you subtract that compound event minus the 2012 is pure wind, the compound is wind and rainfall. So if you subtract them, then you are actually focusing only on the rainfall. So you can see that where is the area that rainfall is making a difference. And you can see, obviously, the biggest difference. There are differences in the upper watershed, but look at this. This all area here is driven mostly by rainfall, or at least rainfall has a major impact. Lake Pontchartrain is a little bit, maybe about 10 centimeter difference or so, but the coastal area is completely numbed or completely unaware of rainfall activity. So you can actually see where is the coastal zone from the transition zone from the inland zone. You can do the opposite by saying, how about if I subtracted this is for the after sea level rise. You can see that actually is pushed further up. With sea level rise, is pushing this transition zone further up. And then that's what the vegetation cover as well. Now let's do the opposite. Let's subtract the compound event from the 2016. So basically, if you take the rainfall out, you can see that this is wind dominated. So as we expected, the entire coastal is mostly wind dominated. Rainfall doesn't play a whole lot of role. Again, this is the transition zone, and then the upland part, wind doesn't do much to it. So again, you can actually delineate where is the coastal zone from the transition zone from the pure hydrology zone when you do these kind of analyses. And then where the boundaries of that the transition zone is not static, it's actually gonna change with time, it's gonna change with sea level rise, and it's gonna change even further if you lose that vegetation. So you can see that when you lose that vegetation cover, the areas that is gonna be dominated by wind migrated inland significantly. All right, I'm going to switch to the last topic, is a new model that we are migrating our models into the flexible mesh domain, so that we are going to use that for forecasting. So I'm going to switch for a second here. I hope that my internet's still working. It is. So this is work is done by Laura. She's my PhD student. I think she was lost. How do I switch? Let me go here. Didn't switch. So how about now? Yes. Laura was actually a Summer Institute fellow last year, and so that's part of her PhD work. So she put this story map where we can actually look at how the model is calibrated. So you can see here, if you click on any point, that you can see the model discharge versus the measured discharge for 2018 and 2019. You can scroll through the different locations. Actually, the model is doing a fantastic job of reproducing the observations. You finish the river, and you can actually go to water level stations. Again, you can look at the different locations on the river for stage, both calibration year 2018, validation 2019. And then there is a massive number of stations in the coast, in Louisiana, called CRIMS stations, coast-wide monitoring reference points. A ton of water level and salinity stations in here. She did all that. This is another set of points. We also have USGS stations that we calibrated the model. You can zoom into each one of them to look at calibration and validation years. And then at the end, after USGS, I think we have a few NOAA stations as well. So this is the model we're planning to turn into operation mode. Let me scroll over. So That's what Laura did also, is made that model operational. So we set up that system to give us a 1 week forecast. But we go beyond what the what NOAA produces in terms of forecasting tool, because we are going to go into a little bit of ecological forecasting. So we want to forecast not only water level, salinity, and temperature, but we also want to forecast, for example, sediment transport and maybe some select water quality, which is something that is not necessarily a focus or imminent coming out of the National Water Center or other NOAA entities. But that's what Laura is working toward. This is the two models that I showed earlier. We are also converted them into operational mode. The larger scale model, we run it. It takes about less than 1 minute to run for 3 days, and it gives us the conditions, the boundary conditions for the regional model. The larger model gives us only water level and temperature. But then once we go into the regional model, then we add these other parameters. This is the current architecture that we are using. I didn't intend for you to read all the individual boxes, but just I will give you a quick overview of the system. The imports from here, some of it is coming from GFS in terms of meteorological input for both hindcasting and forecasting. We also have MRMS, which is a rainfall product of pretty good resolution, I would say. We also have national water model output for the Mississippi River that we use it to supplement what the National Weather Service gives us. And then for the Gulf Atlantic model, this is the hindcasting part that we use it to drive the hindcasting of the regional model, and the forecasting drives the forecasting of the regional model. So we have both products coming from the Gulf Atlantic model into the regional model. We produce the hindcasting piece and we compare it to measurements. We also can produce, as you can see, because we have a lot of details in there, we can look at velocities coming out of these exits of the Mississippi River. So we're trying to use those also for management, because if we can forecast certain conditions, now a lot of people who are doing oysters, commercial oysters, they do it in what they call mobile suspended beds instead of on the bottom. So if we actually give them information with sufficient lead time, they have the opportunity to actually move their beds so that they don't get damaged. I'm not an expert in oyster, but basically, if you subjected oyster at the wrong time to overly fresh water, they can get diseases in them, and then they can be actually quite a big loss for these oyster fishermen. This is also, we have a lot of details around, this is a navigation corridor. So it's very important for us to understand the conditions of the Birdfoot Delta or the Mississippi River Delta, because it does have a substantial economic value. So we want to have a lot of details of water levels and salinity in terms of its ecosystem value, as well as also navigation importance. So I'm going to close it now here talking about engaging going back to the concept of co-production, engaging the managers through that co-development process, actually help them to buy into the tools that we're going to produce, because they have been involved in every step. So that increases the possibility for them to use it in their day-to-day activities. It's also very helpful when we try to translate the model output. You can always still have all the scientific output to communicate with other scientists and engineers, but if we can translate that into socioeconomic indicators or indices that they can use, that can make it much more helpful and informative for the decision-making process. Models, as many of you are aware, they are really good to ask these what-if scenarios and create different scenarios so that we can evaluate trade-offs. Unfortunately, for most coastal systems, it's very difficult to find a specific strategies or scenarios that are good for everybody. So it's very important to evaluate those trade-offs. And finally, that real-time forecasting piece, it can be actually quite helpful if we include in it parameters that can actually help people to react if we have enough lead time. So with that, I will close, and hopefully I can have a few questions that I can try to answer.